Let's talk about reboots and how to make them boring. It was not a boring subject, and now it is, for us at least. So we're talking about who am I, about Cloudflare network, about how Cloudflare works on high-level edge versus core, about our team, about our edge pops. And then we're talking about uptime, why we reboot servers, how to reboot all the servers on the edge. I will talk to you about one kernel upgrade that we had, how we used that to automate ourselves, and then how we rebooted the servers again, now the boring way. And then there was another kernel story. And then further improvements, what since then, and some takeaways for you. So I've been working since 2003 with Linux. I started with LTSP, Linux Terminal Server. Like in 2003, I was working already with PXE, roots, remote desktop over Linux, using like 386 and 486 server machines to connect to a Pentium 4 with 2 gigabytes of RAM, running Firefox. It was like a way of democratize internet access in small cities, small places, like poor places, giving a full laboratory of Linux with the minimum resources that we had. And with this LTSP server, there was Squid Cache to make it work better, and so 2003. And then from 2008 to 2016, I worked in a university in Brazil, doing all kinds of since racking servers, installing and managing LDAP with 100,000 users and so on. Eventually, I was building Cloudflare internally, Nginx server with TLS and some origin servers, and then I joined Cloudflare, where we have origin servers, and then started working with Salt, debugging Nginx, Nomad, building clusters. Who uses Cloudflare here for personal stuff? Let me show your hands. And for work? Sorry for the trouble that I caused it for you. So Cloudflare is an Anycast network, is a CDN and security company these days. We have more than 300 cities where we have servers. The numbers that I have for you is that 60 million requests per second on average, Q2 some months ago, and almost 40 million DNS queries per second. So just have an idea of the scale of the network. We have servers in what we call edge and also core colos or pops. Edge pops are the ones that are close to the eyeballs. So we have those in 300 cities. And core servers, core colos, we have in 3 locations, 3 in a region for HA setup, and then there's a 4th in a separated core HA configuration. So for this talk, we're talking about edge, where we have pop serving requests to eyeballs via Anycast. So we are doing mostly stateless stuff. So CDN, the traffic that goes over the CDN and is going to your origin. So it's mostly not stored in state. We have some state these days, but it's not 100%. And these are bare metals. So we have to manage servers. We provision and install the servers in these locations. And the services, they are running mostly over systemd, and there are some services that are running containerized too, but majority is systemd. For the Edge SRE team, we have 3 regions here in Europe, in Singapore, and some people in Sydney, and also in US and some places in US, and we use the follow the sun. So we are on call when the weeks that we are on call from 9 to 5, and we try to all the time we do some operation of the edge, but we also improve the platform and try to automate ourselves out of the job. And failures that we usually see and debug, they are impactful for customers because they are like in the first mile, they are close to the eyeballs, customers and users. Our edge pops, they are from a SRE perspective, that is not a networking team perspective. They are mainly two types of nodes. the data center management machine that is running the netboot, some saltmaster for configuration management, the monitoring over Prometheus, and then the metals that are the compute servers. They are receiving the requests, the packets from the customers, handling the requests and finding your origin, caching, etc. So they talk to the routers via ECMP, where they are tracking traffic. We have a load balancer that we call Unimog. We blogged about this some time ago. We use this XDP to use the network device to direct the traffic to the correct server in the POP. And we have been using Consul for service discovery. There are also some internal APIs. And the most important thing is that every metal is the same. Not every metal runs every software, but they can run every software. The majority of the softwares are running on every metal. There are some, like just some service discovery that we can run something that is not everywhere. But what makes this work possible is that everything is the same. We can reboot any metal at any time, and other metals will do the same work. So about uptime. Uptime was cool. I found this Linux kernel archive, the kernel.org page from 2004, from 2005, saying, oh, the uptime was 6 months. So this was the last page that I found in archive that had the uptime because it was cool in 2002, 2003, 2005 to say the uptime is like 6 months. Oh, great, Linux is stable. At this point, we were past that, but that was 2005. 2013, there is this Ars Technica article about a machine that was used for 16 years. It says that it booted when Macarena was playing on Billboard. So it's a novel file server, so something local, probably forgotten. But there are people that are still on Reddit saying, oh, my uptime is 1,000 days. So for some people, it's still important. But we reboot servers because we want to upgrade the kernel, because vulnerabilities, because there is a new Linux distribution, because there is some changes that we have to apply that will break if they are applied in a running system. So changing disk layouts, changing the port binding. We have cases where we had to bind port 443 in one server, and then we move to another service. You cannot do that live. Reconfiguring routing parameters and other complex changes that it can cause impact, so you just reboot. Firmware upgrades also. These days, kernels have lockdown methods that don't allow upgrading firmware anymore on live systems, so we have to reboot. And also, there are PCI compliance says that you have to update everything in up to 30 days. So if you just reboot machines, you're sure that you don't have libraries open that are not installed anymore. So it's a simple way of being compliant. Just reboot and everything will be updated. There's this talk from Ignat, Engineer's Guide to Linux Kernel Upgrades, where he talks more about how it's simple and secure to upgrade the kernel. It's more secure than upgrading any software because you are powering off the server, so there is no service there. So kernel upgrades are not risky if the service is offline. And he also mentions the number of CVEs that's patched on each release. So take a look at Ignat's talk. So yeah, we have hundreds of POPs. We have to reboot machines. So how we did that, like after I joined it? It was the exciting way. And the exciting part is the opposite of the boring subject that we bring today, because it was like a team building exercise. Everyone in the SRE team was doing these tasks over the follow the sun. So it was not like 24 hours doing that, but it was during my shift. Someone was assigned to do this in like 10 columns. And then we disable the call via anycast. We execute a few tasks. Could be like wipe all disks and reboot. Could be change, send to apply some firmware upgrade, I don't know. And we use it salt. We use it code change in Git. Sometimes you have to send something to Git and modify how to work it. So the multiple times of different ways of doing the change. Then you reboot. And then boots take like 5 minutes, 10 minutes from post to systems up. And then you wait, and then 10 metals are back, and then 5 minutes later, 30 metals are back, and then 2 hours later, okay, 5 metals are missing. Then you go and try to find why are they missing? Try to fix, and okay, now I fix it. Then enable services, health checks. It's too late already because East Coast is waking up, so we have to bring back the capacity because everything in the region is getting overloaded, and it was like 8 years ago, 6 years ago, we didn't have the same level of automation of network traffic that we have today. So it was compounding problems, and we had to do this fast. The exciting part was that everyone was doing it, and then you had a deadline. The deadline is like 3 hours. You have to finish that. If you don't finish that, it's an instant. So that was the exciting part of the thing. And it was like hundreds of posts, as I said. And it was, the process for everything was taking from 20 to 40 days to complete by 2018. And we had this like 3 or 4 times a year because new kernel, there is a kernel vulnerability. There is a feature that we want to release that requires new IP addressing. Anything that, okay, you have to reboot everything. It was planned. The SRE leadership said, okay, we are going to execute this. It will take a month of work. I will have to reduce my workforce capacity by 1 month doing this. So it was a complex process. And then there was one of these upgrades that updated to kernel 4.14, 4.14.58, and that started crashing. 1 machine a day, 3 machines a day. Eventually, we got like 20 crashes a day. And that was on the time that we had to manually enable each machine because, okay, we rebooted during the planned reboot of the quarter, and then everything was working for some time, 2 months, 3 months. So then you start having this problem like 20 times a day. We had already planned on how to automate that part, so we were doing that, almost ready to deploy that. So, okay, we have to deploy the automation to enable the machines, and we did it. And in the end, there are multiple kernel bisections to find the bug. To this day, I don't know if they really know the bug, but we, as a comment that I put in an internal blog post, this is our cow's monkey. This kernel version made, okay, we have to change how we have to automate the process, right? So it was a way of saying, okay, no more manual tasks. And we automated ourselves first by the Metal enabler service that, so we had a key value store before that we called, that was Kyoto.com, KT. And we were migrating to Quicksilver, our own version of the replicated object store. It was really like 3 months before we finally finished the migration. That took like 3 or 4 years to develop the tool. And Quicksilver was already planned to like be self-sufficient, to be able to rebootstrap if failed. Because one of the technical debts that we had with the previous one, it was we had data corruption crash. And we had to manually fix the machine, and we kept doing that despite attempts to automate. There was, okay, we are going to deploy this new thing soon. And then eventually we deployed, and 3 months later, kernel started to crash, and then, okay, we have the tooling, we can automate the Metal enable. So we didn't have automated our health checks for machines to enable itself because we didn't need, because we had alerts to say if something was broken. Then eventually we brought health checks. And then when we are enabling machines automatically, we also create a way of disabling machines automatically to leave the cluster and go to a reboot. So this automated more automation because then we have a way of disabling and enabling machines. So the next thing that we automated was, okay, now we have to reboot everything. Let's schedule reboots for all machines. And that was called RudyMog as a joke with the Unimog load balancer. So it was just a wordplay. It was scheduling reboots over a 29-day cycle. And it's 29 because it's a prime number. Then you get one node ID, mod 29. You get a random distribution of days. So every machine had a specified date to reboot based on the internal node ID. And they were triggered by a 16 timer. So we did some evaluation that we had like a very well distributed number of machines rebooted per day. So we could just enable that on systemd, so the machines disabled themselves and came back. The other thing that we automated with the first tooling that was RudyMog was the changes that we had to apply. So we created three places to include changes. So the before reboot, so the machine say, okay, I will reboot today. It's my day of rebooting and disabling the services. I'm running some scripts that are in the pre-reboot change phase, so it will do whatever you want. Wipe disks, change some configuration in BIOS, I don't know. Then there is the reboot phase. The second phase is after the reboot, it can run a different script that you can also include for that release. And the third place is changing how we configure salt. So that code is from salt. It's Jinja code to say if it's before. If it's after this release that we call 2023 10.03, that is 3rd of October, 3rd of January 23. If it's after this release, it will apply this change to ulimit in systemd units, whatever. If it's not, it will not apply this. So this is a way of putting in code the things that we were committing on every new call. So we created a way of three places where we can put configuration, and then that was a way of rebooting every machine on a timer. Eventually that worked, but as I said, there is a day to reboot. If the day passes, the machine reboots. If it fails to come back, it will not come back. So then we had to create a second thing that is what we call boring reboot server. That is a coordinator. It's not sending the machines to reboot, but it's getting a queue, and the queue and allowing machines. So machines join a queue, they are authorized, they reboot themselves. If they don't come back, they will get a lock for reboots, and they will not come back, and they will be pending some investigation why this machine didn't come back. Is it configuration manager failure? Is it hardware failure? Then we have ways of identify why we have failures, what happened, and which machines are missing from the cluster, and then we can investigate that. So, of course, there was also a mascot. So this was what we were doing before, pressing buttons, and then we get the boring reboot to press buttons for us. Then, 1 year later, we had the boring way of rebooting. We didn't have to drain POPs anymore. We had the tasks that we were executing manually. Now we were able to specify them in configuration management via the things that we built in RudyMog. Then we had boring reboot server to know which methods rebooted and keep the queue and see how many methods are missing. Then we had to review servers. We built Reboot Rescuer. That was a tool that was trying to revive methods, but not every method comes back because of bad PSU, bad PMC, any reasons. So we still had to do this, recover some machines that failed to boot. The enable services part was now a script. and then we were running this for multiple POPs in the same region during maintenance hours, so we didn't need to repeat for next POP. And then by this time, we started making like a quarterly release where each engineering team that had to apply a change, they could get information from us how to include a change, what to execute, where to include in the configuration management. Eventually, this got into the documentation page and they can do themselves. So we just sometimes help to see if it works correctly. And then like some months later, some days later, there was an emergency kernel upgrade because of Linux SEC vulnerability by Netflix. And we were automating things for more than a year already, but we had the 29 days reboot cycle. But this kernel upgrade was important because there was risk of crashing the machines if we what's the word? If it was about to become public, if it was used, it could crash every machine. So, okay, we have to do an emergency upgrade. But 1 year before, we had a kernel upgrade that crashed every machine. Not every machine, but 20, 30 machines a day. So what we do? So with the automation, we were able to quickly evaluate that, okay, we can. So the first 40 hours of the kernel release were like very small batches, what we call, we have multiple release stages. We have what's called dog fooding, and then we have the canary colors, and then we have the tiers. So the internal tier setup means that tier 3 colors are like 20% of the edge, and the other tiers are like 80%. So we had automation for reboots. We removed some restrictions of reboot only on maintenance hours. We allowed to reboot 24/7, and those colors we've reduced number of machines. And then we were able to, like in 40 hours, we released like 10% of the edge. We got confident that the kernel was not crashing in the machines that we had. And then we released it. In 72 hours, we were able to get to 90% of machines running the kernel with the patches. So from what we had 1 year before, it was a big improvement, not having to reboot every machine to get the new kernel. So from 2019 here, we have been improving how we do the automation. So for the boring reboot server, initially it was everything was a metal. Then we had more server roles. We now have some storage roles with persistent state. We also have a way to detect that if those metals reboot, they will crash, they will break will cause too many shards to be missing. So in the end, we have multiple reboot queues for each node type. We also have, for example, some GPU nodes that are also different. It's a machine, it's the same metal type, but they are different resources. So we don't allow every machine with GPU to reboot at the same time. So we have some capacity in the cluster. So those fixes were, these were added by Thomas and by Rob. Then we have non-deferrable reboots. That was a feature to allow a machine that has a broken disk, for example. We can detect the disk is getting broken. Instead of just crashing the machine, we can say, oh, I'm going to reboot, I will mark this disk as broken, and I will come back without that disk. So that was by Sergey. Then we improved a little bit on the maintenance hours by having the dynamic maintenance hours based on the historical CPU usage by PME. And as I mentioned before, we had Reboot Rescuer to try to recover machines. Casinat and Jaril helped with that. But it's not perfect because BMC is broken, because machines, PSU1 stops working, and then PSU2 is not able to make it work. So we still have some cases where we will have to try a little bit more, and then, okay, this metal just will not work anymore. Then we have to get someone to fix it. In the edge clusters, in the edge POPs, we improved how the service enable and disable scripts work. We included more and more pre-flight and health checks. Pre-flight check is before we enable services, we validate that every condition is there, like every database that we need is there. The Salt was able to apply all the changes correctly, so there is no failure on anything that we know. And then we enable services, and then for some minutes we run some health checks, CDN requests, and check other services are working correctly. Anyone from the company is able to provide a health check and pre-flight check. These are ways of ensuring that we are not enabling a machine that will be broken. So the machine, if the machine is broken, it will re-disable itself, and then we have to investigate why it's failing. The other one that is important is the using of systemd target. We use it to have every service started by Salt configuration manager. So just Salt machine boots, Salt starts the service, and then if it's a backend service, another machine in the same call will connect to that. But if the service is started but data is missing, the other machine will not know, so you are spreading corruption between the machines. So we created a target where this target will be started and enabled only after everything is complete in the machine, and the health checks and pre-flight checks will ensure that the machine will disable itself if it detects failure. So we implemented this target, and we are able to migrate most of the systems that are front-end, what we call front-end services, to this target. And this created a cultural shift on how to use Salt to configure. So this moment we have services being installed in this target, not being started, and then we start the services and when everything is ready as a big on-off switch. For the process, internal process, we now have reboot releases that happen every 28 days. So they start automatically on the date. So the previous ones were like September 5th and then October 8th, and they will just get 28 days after a seed version, a seed value. So we always have this happening. If some engineering team wants to deploy a change, they will have to get the next release and then make the required Salt configuration management changes to include their changes there. They can test. There are a few ways of testing the change, and then just wait for it to go. The release start is staggered, so we start in the first day for what we call dogfooding calls, and then we have 2 or 3 days later for the canary calls that start getting customer traffic, and then 7 days later for the first non-canary calls, and then like 14 and 21 days later for the next step. So if a change is broken, we have like a week to detect before it goes to a large amount of eyeballs. So this is mainly to get regressions. I don't think we ever got any impactful change being reverted, but we detect regressions this way. The servers in the dogfooding calls, they are rebooted every 5 days. So every 5 days they reboot and they reach uptime. So if there is some regression included, we will find out before it becomes a widespread problem. They also get the firmware and kernel updates immediately. So there's a new kernel. These metals, like the first 2 stages of release, will get a new kernel and the new firmware upgrades. So we are able to identify if they are broken or not. The current alerts that the reboots are being started and managed automatically, and they can do, engineers can include changes automatically by themselves, and we don't have to watch the deployments anymore. For alerting, now we have alerts if too many nodes fail to enable for an X amount of hours. So if there are, I think it's 200 or 300 or 400 metals failing to enable, there's something that is wrong, that is a widespread problem, so we investigate. And also if we have too many nodes with uptime for more than 45 days, it's because the release queues are being blocked, and then we have to investigate why it's the case. We had a few regressions that we had to investigate because of this. This is the main Grafana that we watch for release completion. So when I took the screenshot, it was like at 25% of the edge running the new version, and it was 4 hours to start the next stage. So it's mainly to find out if the release is done and if the engineers can remove the salt changes that they had in the code. So the takeaways of this: identify and automate as much as possible as you can, the toil, and automate that. We had an estimation that we had one person working on each region for this reboot automation by 2018. So that's like almost 500 hours of work per release. And the SRE leadership had to approve that, okay, we're going to lose this person for a month. It was never the same person, but it was rotating first. And then our automation of reboots allowed releasing things that would be difficult before, that would take multiple years. We were able to release like in a month. For example, we are always up to date with the kernel that we have. The kernel team, the Linux team is also releasing like a kernel every time that there is a new version. They prepare and they ship it to the dogfooding colors, and if they are happy, they progress everywhere. And then when the machines reboot on their reboot window, they will get a new kernel. And this is safe because the traffic is draining, so there is no risk. There is lower risk than software release, for example. Just for an example of the timelines that we think, this is from when Bookworm was ready, internal blog. We had from Bookworm release to everything on the edge running Bookworm was 87 days, including the time that we spent evaluating performance regressions and everything else. Of course, we started working on that a year before Bookworm was released, building the images and allowing the engineering teams to build packages for Bookworm. But at least the previous iterations of Debian release, we started later. So we started the release after the version was available, and then creating all the automation, the tooling, the tool chains, and enabling people to build packages. And then eventually 1 year after Debian was released, we were able to reboot everything. So by not having to do the reboots, we are able to at least put more focus on, okay, the SRE team is building the base, what we call base image for the new Debian as soon as we can, and when it's ready, we are pushing for the changes for updating the Debian, for example. And so create methods for draining traffic from your clusters. So being able to drain the cluster is important because you're going to reboot machines every month. So you have to have reliable ways of draining traffic. Then you are going to be ready for crashes too, because then you have no way of disabling that server, so you know that the server that crashes is not going to affect everyone else. Create pre-flight and health checks and end-to-end tests. So then when a machine fails to enable, it will be able to kill itself. And reboot all the time to catch regressions, because regressions happen. And we find them all the time, a software that's crashing to start, or a dependency that is not working as expected. And then even more, reboot all the time by getting some nodes that will reboot as soon as they get a change, so you test the changes automatically as soon as possible. And I think that's it.